Hello, and welcome back to another Earth Science video here with Mr. Farney. This is our third video in our plate tectonics section. In this one, we're finally going to get to some earth-shaking material here where we're seeing different interactions of different types of continental plates, oceanic plates, as they move around, as they kind of collide with each other, they separate, they slide past, all these different things. We're going to briefly look at some examples of them, where to find them around the world. We'll get more into the mechanisms behind like earthquakes and volcanoes and things like that in a later unit. But for the purposes of this unit in this video, we're just looking at how these different types of materials, whether you're oceanic lithosphere, you're that basalt, you're that heavy dense material, how that's interacting with our continental lithosphere, the less dense, fluffier granite, how they interact, what happens when they interact, and the different types of formations that can occur through this interaction. So again, back to our buddy Alfred Wegener. He hypothesized that the Earth was made up of different puzzle pieces. We've taken this idea, we call them plates. There's around 20 of them, and they're huge pieces of Earth's crust that fit together at their edges. And it's at these edges where we see a lot of these different tectonic formations and a lot of this activity occur. We have multiple different types of features. We have volcanoes. We all know volcanoes are exploding mountains where lava comes out. Earthquakes, where the earth shakes like an Etch-a-Sketch. Trenches, these really deep parts of the ocean that we find at the boundaries between some of these plates. Mid-ocean ridges where we're making new basalt, new oceanic lithosphere, and rift valleys where continental crust is really slowly pulling apart from each other, creating these new really deep valleys. So all these different features can be found across different tectonic plate boundaries and be depending on the interaction between the two plates, whether you're ocean-ocean, ocean-continent, or continent-continent. Whichever the orientation, you're going to see different types of features found at the three different types of plate boundaries here. So again, just to reiterate, our three types. This first one that you see here, where we have the plates moving apart from each other, we call it divergent because they're dividing. Everybody always say, take your hands like this, go like this, divergent. We're dividing apart from each other. The second one there, letter B, we have one plate going into the second plate. This is converging. They're converging onto each other. So if divergent were thumbs out going out, convergent thumbs together going together. And the last one is transform, where you have two plates sliding past each other. One's kind of moving forward, the other one's kind of moving backwards. So I suggest go with your hands, go like this. That way you can have a kind of a good visual understanding of what's going on at these three basic plates. So let's talk about that divergent plate boundary first, where our arrows are pointing away. They're moving away from each other, our divergent plate boundaries. You have two tectonic plates moving apart. We get different types of volcanism. We'll get earthquakes here. High heat flow, which makes sense because if we're talking mid-ocean ridges where the plates are moving apart, these are areas where you probably might have new oceanic crust forming, maybe new continental crust forming. So we have a lot of heat here, a lot of heat coming up from our mantle to the surface. Primarily, we find this type of plate boundary at the seafloor. However, there is one or two locations continental-wise where you can find divergent plate boundaries. Mid-ocean ridges, that's the main one that we're going to concern ourselves with when we're talking about divergent plate boundaries. Remember, our long mountain chains, because of this tectonic activity underwater, magma is coming up from our mantle. Remember, this whole idea of plate movement and magma coming back up from the mantle, it's all driven by convection currents in our asthenosphere. Remember, that was kind of the lower part of the mantle. We have that convection cell pushing all that hot material up back toward the surface. That's why we have a high heat flow at our mid-ocean ridges. Rift valleys, there's one in Africa called the East African Rift Valley. They're long, narrow depressions that form either in the center of mid-ocean ridges or between two land masses when they're slowly pulling apart from each other. So there's a lot of information here that you can pull from divergent boundaries depending where you are. Are you on the ocean? Are you on the continent? And then really the mechanisms that we learned in our last video about how that magma is coming back to the surface, generating that high heat flow. So again, if you're in the ocean, if you're talking about an ocean, that means you have an oceanic plate interacting with an oceanic plate. Basalt. We got that ocean going on there. This is where you're going to find the mid-ocean ridge, like in the middle of the Atlantic. The mid-Atlantic ridge is a great example of an ocean-ocean interaction. We're talking continent, we're talking about rift valleys specifically, like the East African Rift Valley that occurs when you have, those two plates pulling away from each other. Normally, the tectonic activity here, it's not a lot of volcano-like activity, probably more specific right now, looking at how the East African Rift Valley is. It's a lot of just earthquakes because the earth is slowly tearing itself apart. It's as if you were to take, and let me grab here, like a piece of paper, this is a little Post-it note, and if I were to just kind of slowly, very, very slowly try to tear it. See, that was a very fast tear, but if I were to kind of put them back together and just slowly, as slow as humanly possible, try to separate these. That's kind of what's going on in Africa, the East African Rift Valley, is I'm slowly tearing that piece of paper apart. This is a picture of the East African Rift Valley. You can see here on the leftmost thing, it shows you where in Africa it is. So it's the east portion of Africa there. It goes from the Lake Victoria all the way up toward the Red Sea. It looks like parts of it, there are some parts maybe south of Lake Victoria, but primarily it's Lake Victoria all the way up toward the Red Sea there is the area of interest that we have right now. On the map on the right, you see all those little red dots. Those are areas of tectonic activity that's occurring. So we have a ton of tectonic activity going down like the middle of kind of like your screen here from the Red Sea all the way down to Lake Victoria and then a little bit further south. So this whole area, this is the Rift Valley. That's that slow tearing of our continent separating. So give this several, I'm going to say 10, 20 million years, Madagascar, it's going to have itself another island buddy because there'll be a sea that probably forms all the way through here. And Lake Victoria won't be a lake anymore. Maybe future generations, we'll call that the Sea of Victoria. Who knows? So that's the first type. Second is convergent boundaries. We're converging onto something. You have two boundaries pressing into each other. They're moving toward each other. Depending the interaction here, this is how you could form trenches. This is how you could form island arcs. Both of those trenches and island arcs you can find off of Japan. We'll see a picture of that in a minute. This is how you can form mountain ranges hundreds of miles inland, similar to like the Sierra Nevada and the Rockies in the United States. Or I believe the Andes Mountains in South America is a really good example of this. Or folded mountains, like when you have the Indian plate colliding with the Eurasian plate, creating some of the tallest mountains in the world, the Himalayas. So that's what we're looking at here for convergent. We have plates moving toward each other. Now, one of the words that we're going to learn that goes along with this is subduction. We're going to come back to this in a second, but this whole idea of our first two interactions, our ocean-ocean and ocean-continental, has to do with subduction. Who is going to win the subduction game? If you have two plates colliding with each other, how do I know which one is going to go underneath the other one? Well, it has to do with which one is more dense. So we learned in our last video that our oceanic lithosphere is made out of basalt, which is a much heavier, a much more dense material than our continental lithosphere, which is made out of granite. It's much less dense, it's lighter. I like to use the word fluffy, even though it's a rock, it's fluffier. So when these two plates collide, the more dense material, the oceanic lithosphere, will subduct underneath our continental lithosphere. And that's what's going on in this picture. The oceanic plate, which is colored in gray, moves toward our continental plate. And since it's more dense, it'll sink underneath it and return to the mantle or our asthenosphere. As it returns to the mantle, it's going to start melting because remember, our temperatures are much, much hotter deep underground. So that plate will start melting and that magma will slowly start working its way up toward the surface, creating mountain chains hundreds of miles inland. like the Andes Mountains in South America, or potentially, you know, the Rocky Mountains or the Sierra Nevada mountain ranges in the United States. So that's subduction. We'll come back to that in a minute. Firstly, what happens if you have the two oceanic plates collide with each other? Well, remember, the whole game is who is going to subduct underneath the other. And if they're both heavy material and they're both dense, they're going to collide into each other like this, but then they're going to start pushing each other inward really, really hard at this subduction zone, creating really deep trenches with an island arc adjacent to them. So you can see here, we have, this is, I believe, a picture of Cuba here. We got Cuba, we have Puerto Rico here. So there is the Puerto Rican trench right there. This is the North American plate here. It's oceanic. And then this is the Caribbean plate here. That's also oceanic, and they're colliding with each other. So it's a really interesting collision that's going on very close to the United States. And it's creating this really deep trench. Now, some of the North American plate is able to get underneath the Caribbean plate. And in doing so, that material will begin to melt and work its way up toward the surface. So the Virgin Islands here, Puerto Rico, maybe even parts of Hispaniola that's there, that wouldn't have been able to form if you didn't have the North American plate trying to go under the Caribbean plate. That's also why areas down here like the Virgin Islands, Puerto Rico, it's very tectonically active compared to other things in the Atlantic Basin because you have this subduction trying to occur. So that's a really interesting feature we need to just be aware of when we have these oceanic plates interacting with each other. It's the same idea as how the Mariana Trench right off the coast of Japan is forming. Highly tectonically active. Here's a picture of the Mariana Trench. In the picture, it is this really deep purple here, and I believe the deepest part is at the very south, right here, where we have the Mariana Trench. They're right there labeled with the arrow. Because we have this trench forming right here with the oceanic plate trying to go under another oceanic plate, we get all of this different island arc formation occurring right behind it. This island arc, these islands are formed because of this oceanic plate trying to go underneath another oceanic plate. And you can see here, if we go more west, we have more subduction occurring. So because of all the subduction that's occurring up there in the Northwestern Pacific, it's very tectonically active. It's why Japan almost gets as many earthquakes as like California and some places in the United States. But a really good example of oceanic convergency is the Marianas Trench right off the coast of Japan here. Our other type of convergent is Oceanic Continental. This is the one I know, the one I think of when I think of convergent plate boundaries. You have two colliding, one with low density, one with high. Remember, our low material, it's continental crust that's made out of the granite. Our heavy, our high density material, our oceanic crust right there. When they collide, the heavier material, the oceanic one, will subduct. It will go underneath our continental crust. It'll begin to melt, and that material will work its way back to the surface, making mountain ranges at the surface of the Andes mountain ranges, perhaps the Sierra Nevada or the Rockies. You also get a small trench feature right off the coastline. This is not nearly as deep, not even close, as if this was ocean-ocean interaction. But because it's ocean continental, there's still going to be some bending of the material, just not nearly as deep as you would see in that ocean-ocean interaction. I like this picture because you can visibly see the trench right off the coast of South America here. It's this kind of deep, dark line that almost looks like it's outlining South America going all the way down. And as it subducts underneath it, we get this mountain range that's right back here. You can see kind of like the white snow caps on the map there. That mountain range is formed because of that subduction of the oceanic plate going underneath the continental plate here. That Pacific plate going under the, I believe that would probably be the South American plate. That oceanic lithosphere going under the continental. The basalt going under the granite. These are all just words saying the same thing. Adjectives. How can we describe things maybe slightly differently? The last type of convergent boundary is continent-continent. I like this one. You have two lightweight plates colliding with each other. So if our heavy, dense material, if they collide, they sink. They create those trenches. Our very light, fluffy material, our continental granite, if they collide, they make like almost like an accordion type thing. So I would be like folding my paper almost like this, if you can see it. I'm making an accordion. If on one side it's continental, one side it's continental, and they collide, I'd be making kind of this accordion type fold that's going on in the mountain range. So the opposite that you would see with oceanic. We get large mountain ranges with this. This is what happened when the Indian plate of 30, 40 million years ago decided to slide and collide with the Eurasian plate. We've got the Himalayan mountain ranges. So right here, this is India, this is the Indian plate. It collided with the Eurasian plate, making our really huge mountain ranges right here, our Himalayas. This is a picture of the world famous Mount Everest. If this collision never occurred, we would not have gotten Mount Everest. So Mount Everest, it's formed because of that continental convergent zone. Really cool, really important. Our last type of plate boundaries, transform faults. This happens when you have two plates sliding across from each other. We can just imagine, for simplicity's sake, one goes north, one goes south. That's a good way of thinking about it right now. They're sliding past each other. You get really long faults because of this, and a lot of shallow earthquakes. I like to think that our transform faults here create some of the largest earthquakes that we could deal with. Because what happens is these faults want to slide across one another, but sometimes they get stuck. And if they get stuck, they are still trying to slide past each other. So this energy, this potential energy slowly builds up more and more over time until all of a sudden, bam, a really fast movement happens. All that potential energy is released, becomes kinetic, and then that kinetic energy is released in the form of different types of very shallow surface earthquakes that can cause a lot of damage. This is why sometimes California is like an etch-a-sketch, because of these plates sliding past each other. Our top tier example is the San Andreas Fault. Now, if I can draw on this slide real quick here, imagine the left side is California and the right side is east past California. This fault goes all the way down toward Mexico and up into parts of California. So we're going to talk about right now why California won't fall off into the ocean. So this right side here is essentially moving south with that blue arrow. The left side here is essentially moving north with that arrow. There is not a lot of, movement laterally between these two plates. They are merely sliding back and forth from each other. The left side, California, moving north. All right, Cal here for California. And the right side, a little more east of California, we're getting more into, like the, Nevada-ish states and things like that. That's going more south. So again, not a lot of separation. They're just moving past each other. So perhaps in 10, 20 million years, California will just be maybe a little more northwest-ish, not falling off into the ocean, not floating away, because it can't. It's part of that continental crust. If anything, like I said, it's going to move north. That oceanic plate's going to keep subducting under California. So this right here, this part of California, it's not going to break off and fall in the ocean. It's not going to break off and float away up toward, out to sea. It's just going to keep sliding past the rest of the continent, going more northwest. So fear not a big issue there. All right, let me remove my drawer right there, get back to my mouse. And I believe this was the last slide. So yeah, in our next video, we're going to kind of recap causes of plate motion. We'll talk about convection a little bit more. We'll learn about two different terms that really drive that convection movement that have to do with how the plates are interacting with each other. So if you missed anything in this video, I encourage you to go back and rewatch it, because there's a lot of stuff going on in here between the different plate boundaries. If you have a question for me, please go ahead, let me know. I will respond to you as soon as I see it. And have a great rest of your day. We'll see you next time. Bye-bye.